Time to look at the second derivative and things that we can find using the second derivative. First is called points of inflection. We'll talk about that, and concavity momentarily. And then we can also use the second derivative, kind of like the first derivative, to find minimums and maximums. That'll be most useful in tables. We'll talk about that here momentarily. But basically, first what I want to look at here is what concavity really means. So concavity basically is a way for us to look at how the function is curving. And the way that we say that is concave up means that if f prime is increasing, so that means that the slope is getting even bigger as we're going along. So like here I have, this would be like a thing with no concavity because we're increasing at the same rate. But if I'm like a quadratic where I'm getting, or an exponential, I'm getting a lot quicker as I'm increasing, that's an idea where f double prime is also positive. If I'm increasing at a slower rate, so kind of like that would be like an ln graph or a cubed root graph, this would be f double prime being negative. Okay, so it's because we're increasing now at a lower rate versus here you are increasing at a higher rate. And the way that we talk about that is just we say that we are concave up or concave down. Easiest way to look at it is that this part here looks like a cup. Concave up kind of looks like a cup, looks like a smile. Concave down kind of looks like a frown because you're curving downwards. So curving upwards for concave up, curving downwards for concave down. Pretty much just that straightforward. Now, points of inflection are locations where concavity changes. So if I'm looking at this graph I have over here, at the beginning we are frowning. This is concave down, but then at some point, all of a sudden, hey, look, we're going back to something that is smiling, and then maybe at the end back to frowning. The easiest way to look at that is think if you are driving a car along that path. This entire time, I'm going to be kind of steering the wheel to the right here. And then right about here, maybe at x equals -1, my steering wheel is going to start going back to the left. That means I'm steering back to the left, and I'm in the smiling mode, and now maybe right around here, 2 or 3, is when I'm going to have to start turning back to the right if I'm following this path. So those places where my steering wheel changes, where I'm going right or left, that's where my column points of inflection occur, the spots where concavity changes. And the other way to look at that is if I kind of follow this around, it's going to draw the f prime graph for you. And notice, where did my spots equal 0? That's kind of what we're looking at. Not looking at f prime equaling 0 as much as where does f prime change, and where do we have maxes and mins, because this is the derivative of f prime. So we're looking at f double prime, the derivative of f prime. So when does f prime's derivative, this orange graph's derivative, equal 0? Again, it looks like it has a max or min around -1 like we thought, and about at 3 like we thought, which makes sense. Those are the spots where you would have had to turn your wheel. So if you think about it that way, okay, I am going downwards, I'm turning to the right. Now I'm going upwards, I'm turning to the left. Now I'm going downwards, turning to the right. So all these graphs end up matching up with each other and being very important. They're all related to each other. So now, to actually use this, let's look at this example and say we want to find the concavity of this graph, x to the 4th minus x cubed. So that is f of x equaling x to the 4th minus 4x cubed. So that means we need to be taking not just one derivative, but 2 derivatives to find concavity. So the first derivative, 4x cubed minus 12x squared, and then take another derivative, 12x squared minus 24x. And the same sort of idea, we're going to look at where does this second derivative equal 0. That's going to allow us to find areas where we're concave up, where we're concave down, and where we have these points of inflection. So points of inflection will happen when this derivative is undefined or when it equals 0. We also have to look at when the function itself is undefined. We'll look at some more of those problems in future lessons. But what we're going to do here, if we set this equal to 0, I can factor out a 12x, be left with x minus 2. So I have points of inflection at x equals 0, and x equals 2. Those are my possible points of inflection. To find whether I'm concave up or concave down, I need to be going and using my number line. This is the number line for f double prime. We know these are the spots where that second derivative equals 0. And just like before, I have these 3 test regions that I need to plug in. So I plug in -1, I would get a negative times a negative, which means a positive. If I plug in +1, positive times negative gives me negative. And then if I plug in like 3, that will become a positive. So concave up regions from -infinity to 0 and from 2 to infinity. Concave down regions would be from 2 until infinity. Just like that, you can find your points of inflection. Let's take a look at another example. Let's say we want to find, again, the points of inflection where you're concave up and where we're concave down. So there's your function. We're going to, again, have to take a derivative and a second derivative. First derivative will become 1/2 x to the 4th plus, that'll be x squared plus 7. Take another derivative, I'm going to get 2x cubed plus 2x. And again, we're going to set this derivative equal to 0. So to do that, factor out a 2x, that's a 2x squared, leaves you with x plus 1. So we have x equals 0 and x equals -1 as points of inflection. I'm going to put them in that order, -1 and 0, because I can then make sure I have it in the correct order when I use my number line. And as I'm doing this, again, I'm going to plug into my factored f double prime, because I'm looking at f double prime. If I plug in like -2, well, this part being squared means this part is always going to be positive. So I can kind of even just really ignore it, if we're being honest, when I'm plugging in these values. So all I have to look is at this part right here. If I plug in -2, I'm going to get a negative value. If I plug in -1/2, that means I'm going to get a positive. If I plug in any positive number, I'm also going to get a positive. So that means, yes, I am concave down here, concave up in these two regions. So concave up from -1 all the way to infinity. Okay? Concave down would be from -infinity until -1. So where did I change concavity? Only at -1, not here. This is a point of inflection. This x equals 0 actually is not a point of inflection. So we need to eliminate that from our discussion because concavity did not change at that point. That is a very common mistake that ends up happening on an AP exam. Only a point of inflection if concavity officially changes. All right, now one final thing that we're going to look at here is with the second derivative test officially. This is another way to find maxes and mins. Basically, if we don't know that we can do a number line like this, so especially with tables, we can use the second derivative test to figure that out. Basically, if we know we have a critical number, we know we have a possible max or min, we can look at the second derivative to determine if we have a max or min. And the way we do that here is if we have a function that is concave up, and we know we have a critical number, well, that means that it must be a minimum. It must be down at the bottom. If we have something that is concave down, and we have some sort of max or min in there, well, it must be a max. So that's the only way I can be frowning and have a extrema, is if it is a maximum. So the easiest way really is just to draw it out just like I did right there, that if I'm getting a max or min and I know I'm smiling, that must be a minimum. If I'm frowning, then it must be a maximum. So again, the way this pops up most often is with table problems. So it would give you a table like this, and they would say, okay, find all maxes and minimums in this from this table. So find maxes and mins, and then they would say classify the extrema. Classify them as a max or min. So places that we could have a max or min, so max or min would occur when the derivative equals 0. So that means that we're going to have at x equals, or these should be, I'm sorry, helps if I draw the table correctly. This should be f prime and f double prime. There we go. So when does f prime equal 0? Well, at x equals 3, at x equals 6, and x equals 8. Those are the places that my derivative equals 0. Well, we need to then say, okay, each one of those. Could be a max, could be a min, or it could be neither one of them. So, as I, again, adjust my problem a little bit, at x equals 3, we look at, okay, what is f double prime doing? So f double prime at these values, so I'm going to say, I'll even write it over here, f double prime of 3 is greater than 0. It's equal to 2. And since we know that f prime of 3 equals 0, so what we're looking at is we know it's a possible max or min, and we know that we are concave up. So if I'm concave up and I know I have a max or min, that means that this guy must be a minimum at x equals 3. Do another one over here in blue. I know that f prime of 6 is 0, and I know the second derivative there is negative. That means we're concave down. That means that we must have a maximum at x equals positive 6. Just that simple. Kind of draw it out for you to look at it. And the last one left, I'll do it up here at the top, is that we know f prime, that color doesn't show up, does it? Well, we know f prime of 8 is equal to 0. So f prime of 8 is equal to 0. So now we look at f double prime. F double prime of 8, well, it's also 0. So that means, because we don't know whether we are concave up or down, that means that the second derivative test, basically it fails. Okay, we don't know anything about whether or not this is a max or min because of the fact that we have, excuse me, both first and second derivative being 0. This is likely going to be a saddle point, but we cannot say for sure. So if you can draw concave down versus concave up to find max or min, that's how you're going to do it with a second derivative test. And again, this usually will show up only with table problems like this one.